Hi, my name is Neil Reddy and this is my report for Lab 1. The purpose of the lab is to apply Newton's fundamental laws of motion into the real world. The focus is on Newton's second law of motion, which is the momentum principle. The law's accuracy is verified by comparing position-time graphs, one created from real-world data observation and the other from data produced using a computational model. A quick result summary is that when comparing the models, the slopes or velocities were nearly identical to begin, but began to drift away towards the end of the motion. This lab is mainly based around Newton's second law. This law explains how the change of momentum of a system over time is dependent on the net forces acting on a system from its surroundings. When no net force is acting on the system, then the momentum will not change and the velocity will remain constant. In this experiment, the system was a marker, and when no net force acts on the marker, its velocity should remain constant. This can be seen in the momentum principle equation, where final velocity is equal to initial velocity when net force is zero. The position update formula also helps explain Newton's second law. For my procedure, I first recorded the motion of a marker rolling at a constant velocity across the table. I then put this video into the tracker software, allowing me to track the position of the marker at set time intervals. Then I created a computational model of the marker's motion by manipulating the starter code in GlowScript. I then created the position versus time graphs from the data collected, and finally compared the two graphs to verify Newton's law of motion. In my experiment, I chose to observe the motion of a marker rolling across a table. It was assumed that air resistance and friction were negligible. The tracking was started after the marker left my hand to ensure that there was no external force. The system was the marker and the surroundings were the table and my hand. The initial position of the marker was 0.0112 meters and the initial velocity of the marker was 0.798 meters per second, and I calculated this at 0.033 seconds. Next, I used the starter code given to us to create a computational model in GlowScript. A ball was used in my code to represent the marker, and the mass of the ball was negligible since it gets cancelled out in the formula. I set delta t to 1/30th since the video was recorded at 30 frames per second. The initial position and velocity were stored as vectors in my code, and then I used the position and velocity update formula to map the motion of the ball, which can be seen in my code to the right. Here's a comparison of the two position time graphs. Initially, the two slopes are nearly identical, which indicates that the computational model is a good estimate for the marker's motion. However, as time goes on, the tracker model appears to slow down. This is due to the friction that the marker experiences as it rolls across the table, which is not accounted for in the computational model. So the main source of error in this lab was the friction that the marker faced in the opposite direction of its motion, causing it to slow down. And here are some concluding questions. What if the axes were interchanged? I chose my axes so that left was negative and right was positive, which resulted in an upward sloping curve. If these flipped, the magnitude of the slopes would remain the same. However, the direction would change to a downward sloping curve. The results of the experiment would stay consistent. And how many forces add up to a net force of zero? It is impossible to tell how many total pushes and pulls acted on the marker to produce a net force of zero, since the marker collides with things such as air particles. The forces that are known are the normal force, gravitational force, friction, and the force of my hand on the marker. Thank you for listening.